Okay.
Okay. Hello, everybody. Good morning. Welcome to our 11th Geometry Topology Summer School. And our first speaker is Rosa Sena-Dias, who is going to talk about action angle coordinates and Riemannian geometry on toric manifolds.
Okay, thank you very much for the invitation. I'm very happy to give these lectures. So, all of the lectures are going to concern some, informally, I would say some, maximally symmetric scalar manifolds. Which are called toric scalar manifolds. And so the reason why they are worth studying, and they have been studied quite a lot in the past, is sort of twofold. First of all, so toric scalar manifolds are simpler than general manifolds. And let me tell you why, because this is at least vaguely easy to justify. First of all, they're classified by some combinatorics. They're classified by convex polytopes in Rn. And so secondly, for me, their metrics are determined or classified by a convex function on a convex set. So it is much simpler than a two tensor defined locally and positive definite and whatnot. Okay, so I think these are the two main items that make toric scalar manifolds simpler. But then there's actually a sort of the other side of the story is that although they are simpler, they exhibit rich behavior. So toric scalar manifolds are what I would call geometrically rich. So I'm being very informal here. And what do I mean by that? I mean that somehow they exhibit sort of generic behavior in many geometric problems that we've looked at on them. So or for many geometric problems. Okay, and so this combination of factors makes them very appealing. And what happens is that they have worked as what I would call mathematical guinea pigs. And there are several instances of this. So let me mention a few. I don't know exactly what your backgrounds are, so some of these may appeal to you more than others. But I think one of the sort of the first things in which they sort of showed power is, so there's a sort of resolution of singularities for them. That's really, very neat. So there's also, people use them to work out things about the minimal model program. They're also really popular with people studying mirror symmetry. So for instance, there's sort of a lot known about their Gromov-Witten invariants. in relation to this. There's people sort of know how to calculate mirrors and all of that. And the last arrow here, which is the most relevant for me, is that there's a neat solution of the existence problem for constant scalar curvature Kähler metrics. On them, which is it's pretty recent. It's something like it started in 2006 maybe. It's due to Donaldson, and it works per surfaces only, so in 2 dimensions. Okay, so there are many other examples, but so I guess that the goal of my talks is to add a couple of really high items to that list. So they're not as far-reaching as the things I've said before, but I want to talk about 2 specific problems in geometry that I think people care about in general in the realm of toric geometry. So let me tell you straight out what they are. One is the existence for Hermitian Einstein metrics. I'm only worried with four dimensions. And the other one is minimal Lagrangian tori. And I will give background for these 2 problems when I get to them. But today I sort of wanted to set up toric geometry, how I use it. So let me start with that. So I don't know whether there are algebraic geometers in the audience, but algebraic geometers look at toric geometries from a slightly different perspective, which and maybe theirs is better known. So I sort of wanted to tell you my setting. So first of all, let me start with the definition. Let me know if this is. I mean, I'll go fast. Let me know if you want me to go slower or faster even. So I'm going to be working on Kähler manifolds always. So for me, a Kähler manifold is a list of the following things. So it's a manifold. It's a symplectic 2 form, a complex structure, and a metric. And they have to be compatible in the following way. So a Kähler manifold is the following thing. So first of all, J needs to preserve the metric. Oops. And this 2 form, which is in fact determined by the metric and the J, is symplectic, which means 2 things. You probably know that, but it means, first of all, that it's closed and it's non-degenerate. So if the manifold has dimension 2D, then the highest wedge of the of the two form is nowhere vanishing. It's a volume form. Okay, so it's sort of a, I guess, silly definition to give because you either know it and I'm boring you, or you don't know it and it's sort of a sophisticated definition. Any questions? Anything I can do to help with this? Okay, if not, then for me, a toric manifold is scalar in the following sense. So suppose you have a scalar manifold. Then we say it's toric if it admits an effective Tn action. And so it's crucial that the dimension of the torus that's acting is half the dimension of the manifold, such that we want the action to be compatible with the Kähler structure. So two things. So the action needs to be holomorphic. So each of the diffeom, sorry. Each of the, sorry, I erased my whole frame. So I was saying that okay, the Tn action, we wanted to be compatible with the Kähler structure. So we wanted to satisfy two things. It is holomorphic in the sense that each of the diffeomorphisms induced by an element in Tn is a biholomorphism, and it is Hamiltonian. And Hamiltonian is what one would require in the symplectic world. So let me quickly remind you what it means. So this means that there is a moment map, essentially. There is a map from the manifold to the dual of the Lie algebra of the torus, which we can identify with Rn, which needs to be invariant. And okay, so here's the definition of the moment map, which is essentially what I'm going to give you now. So, okay, so the moment map is a primitive of the vector field induced by the action. So this needs to be true for all of the elements in the Lie algebra, and this x psi is the vector field induced by the action. So this is, so these are this is what a moment map means. Okay, and it's only defined up to a constant in the dual of the Lie algebra. Okay, any questions? So I guess that the first result we have or the first result I want to mention here is a theorem due to both Atiyah and Bott and to Gilman and Sternberg working independently. And the theorem is the following. So suppose you have a toric Kähler manifold with a moment map mu, then the image of the moment map is a convex polytope of Rn. Okay, so this is essentially what makes toric manifolds simple. There's a polytope associated to them. So this mu m is called the moment polytope, and it's always of the following form. So it's given by an intersection of half planes, which I'm going to write like this. I'm going to need these hyperplanes later on, so I want to give them a name. So this is what we call Li of x. So the moment polytope of a toric manifold is always of this form, where it's even more specific than that. So at each vertex, there are exactly n facets meeting. And what's more, the corresponding normals, nu I, they have to be the normals from the way I wrote them, form a basis for Zn, which is a really strong requirement, but it just so happens that the moment polytopes of toric Kähler varieties are like that. And so such polytopes are called of Delson type. And Delson comes into the story because he proved the following theorem, which is the rest of the classification theorem. He proved that the moment polytope of a toric Kähler manifold determines the manifold, but in fact only up to equivariant symplectomorphism. So the important thing here is symplectomorphism. What this means is that P determines M omega. It doesn't determine G. It doesn't determine the metric. It only determines omega. And I guess algebraic geometers who usually don't have the whole polytope would like to know whether P determines the J. And in fact, it does also. But if you choose the polytope to determine the manifold up to equivariant biholomorphism, then the biholomorphism will not preserve the symplectic form. You have to choose. You either have, it either preserves the J or the omega, but not both. Okay, any questions? Okay, so let me just do some examples. And you can let me know if I'm giving too much, if I'm going too slow in the examples. But so the very first toric Kähler manifold there is S2. Which is just CP1. So there's a J, the usual J, and the symplectic form is the Fubini-Studi one. So it's given by this formula, where Z is this. And if I give you the G and the omega, if I give you J, sorry, and the omega, it determines the G. So it's the round metric, in fact. So, but this is a fact of Kähler geometry. Maybe you would have noticed from the definition, two of those structures. So a Kähler structure is a triple, but two of the structures determine the other one. Okay, so I sort of wanted to go through the map calculation with you. If just, I don't know, I think it's a fun calculation. Maybe you've never seen it. So it's useful to use polar coordinates. And when I do that, well, the Fubini-Studi metric becomes this. And so let's calculate the moment map. So the first thing we need, I have to tell you what the action is. So S1 acts on S2 in the usual way. So like this. And the picture is as follows. So it's the usual rotation. Here's S2. S1 acts this way on the sphere. Okay, so let me do the moment map calculation and let's see together that mu of P is convex. So, so the Lie algebra S1 is just this. And so we need to calculate we only need to calculate one vector field. So let's calculate the one that's induced by this. And it's just this. Oh, okay. It's just this. And this is what we call the vector field dd theta. And we need to calculate this, which the Fubini-Studi metric, or the Fubini-Studi form. And oh, I'm missing an R. Did I miss the R before? Yes. Is this okay? Or should I mean, you just to write down the expression for the Fubini-Studi metric in these coordinates, you need dz. It's dr plus I d r d theta. Is this okay? Oh, I had my sound down. Okay.
Yes, pretty much good detail. Yeah, thank you.
Okay. So this is minus this. And we can calculate the primitive. It's d of this. So this is the moment map. So it's, you can see that it's equivariant. It's this up to a constant. You can see that it's equivariant, and we can calculate the moment map image. It's just the interval 0, 1. So let me go back to the picture. Here's S2. And here's the moment map. If you think of a point here, let's say this one, then its pre-image is a circle. And in fact, all of the pre-images are circles, except for the pre-images of these points, which are just points. Okay, so you see S2 as a fibration over the open interval 0, 1, where the fibers at the endpoints collapse. The fibers are S1s. So schematically, you see this, and the fibers collapse 2 points. And the fibration map is mu. It's not a fibration, it's just a fibration over the open. Okay, so let me do a second example in detail, because it's an example that's going to be important for me. The example is O of -1, which is the tautological bundle over CP1. So what's this? This is just, well, it's above each point in CP1, the line over that point. So a point in the line is a point in C2, but to make sure that it's over the line, I'm going to ask that it satisfies this. And so Z0, Z1 is so this is what O of -1 is. It's, I should separate these examples, sorry. So this is, as I've written it, it's a subset of CP1 cross C2. And CP1 cross C2 has a Kähler structure. It's the product Kähler structure, where C2 has the flat Kähler metric. And I didn't say that, but Kählerness works well with restrictions. So O-1 gets so inherits a Kähler structure from this one. And there is an S1. Oops, what did I do? There's an S1 cross S1 action in here, which is just given in this way. So well, okay, on CP1 in this way, and it seems silly because you could move this factor onto here, because we are in homogeneous coordinates. But the reason why it's not an effective action is that we're also going to make it act here. So this is how how T2 acts on O of -1. And okay, so let's see what the moment map is and what the moment polytope is. So now there's well, first of all, the symplectic form, we can write it like this. It's let's see. Well, you can write it. So the first part we've talked about before. It's this. The second part is even easier. It's and we're going to use polar coordinates on the C2 as well. So let's write each of these like this. Okay, so we have to calculate now two vector fields, and we'll have two components of the moment map. This one is okay. So let's so this one, there is a part on CP1 which is exactly the same as before, because I theta 0 acts now as it used to act on CP1. So there's a dd theta part. And how does it act on C2? Well, it only acts on the first component, and so it's also the same as it was before. So it's dd alpha 0. Okay, and there is the second, so the one that comes from varying just theta 1. And the interesting thing here is that there's a minus dd theta, because e theta 1 acts on this component, and this component is in the denominator. So there's a minus that comes when I change the coordinates, and then plus dd alpha 1. Okay, so what is this? I'm supposed to calculate this, and then its primitive. Okay, so one of the parts is just this together with this, and we've calculated this before. And the other part is easier, in fact, because it's just this. Oops, it's just this together with this. And it's just, it's 2I d R0. You need to convert these into polar coordinates, but that's even easier than the Fubini-Studi metric. Okay, so this is, there's a plus here, sorry. This is this. And the other one, on the other hand, is there's a plus. Is this. Okay, so I can write down the moment map. It's just this and that, and it's up to a constant. And let me choose a +1 here. Is this okay? So we can now calculate the moment map image. Okay, so it's x1, x2. So each of the components of the moment map is positive. And if you sum them, it's unfortunate that it's in this page, but if you sum them, the sum is this plus that plus 1. So it's greater than 1. So the polytope for this is this. This is a non-compact toric manifold. Okay, so it's going to be important in what I say later. So let me give you two more examples which are going to be important. And if you have time, you can sort of try to do the calculations in the way I did them for these two. So there is CP2. With its homogeneous coordinates and the Fubini-Studi metric. And what it is, what its moment map image is just a triangle like this. And the reason why I want to talk about this example is that it makes something important for me clear. So the pre-image over points here. So in fact, let me tell you what the moment map is. But you would need to calculate it. It's I think it's an easy exercise, but it's okay. So what happens here is, if I take a point over here, then the pre-image of a point over here is actually a 2 torus. But once I move to one of these facets, say this one, this corresponds to, for instance, omega 0 is 0, then the pre-image becomes a circle. And if I move towards, say, this, which is where omega 1 is 0, then it becomes a different circle. And if I move along these lines towards the vertices, then the image becomes just a point. So the vertices are the fixed points of the action. Okay. So let me skip example 4. I'm going to have to say something about it. Well, maybe I can just quickly say. And another example which is going to be important to me is this one. And this is going to be, this is a Hirzebruch surface. How can I write it in a way that the Kähler structure becomes evident? Well, here is, it's a bundle over, so each of these is a bundle over CP2, and I take their direct sum, it becomes a rank 2 bundle, and I projectivize each fiber. So it's a fiber, it's a bundle whose fiber is a CP1. And I can write it like this. So these are the part in O. So I'm in fact starting with m equals 1, which is easier to understand. So these satisfy this. And then this is
Rosa, your voice is gone somehow, but can you unmute yourself?
okay.
Now it works, yeah, okay.
Okay. Okay. Sorry, I don't know what I did. Okay, so let me now tell you about action angle coordinates, which is my next topic. Okay, so I mean, if in all of these examples, you can see that there is a special set, which is the pre-image via the moment map of the interior of the moment polytope. And this is where the action is free. It's the open, dense set where Tn acts freely. And because of that, we get coordinates on this open dense set, because if the action is free, then you can interpret your manifold as the polytope cross Tn. And what you so the coordinates you get from this are action angle coordinates, are what we call action angle coordinates. And so what's so great about these coordinates? Well, one of the great things about them is that they are adapted to the symplectic form. So they are Darboux, in the sense that the symplectic form is given like this. And there is another really nice thing about them. In fact, they work well with complex coordinates, although I won't have time to say why, but it translates into the following theorem, which is due to Abreu. And the theorem is that, okay, so suppose you have a toric Kähler manifold. Then if you have action angle coordinates, there is a function on the moment polytope which gives the metric in the following way. It's the metric can always be written like this. Where okay, so this Uij mean the entries of the Hessian of U. And okay, so here I should have. And when I put the upper indices, it means the entries of the inverse of the Hessian. Okay, and a U like this, the U that corresponds to the metric, satisfies three conditions. First of all, its Hessian is positive definite, as you see from this formula, right? It's actually, its Hessian, it gives the entry or some of the entries of the metric, so the metric is positive definite. Second, the U is actually only defined from this formula on the interior of the polytope, because there's the xi's are only defined on the interior of the polytope, but it just so happens that we know exactly how it should behave on the boundary. In fact, minus Li log Li is smooth, where Li I've defined before, its zero set is one of the facets of the polytopes. So on each facet, we know that U is continuous but not smooth on that facet, and it behaves like this. And so it's, and then there is a third condition, which is not going to be very important to us. So I'm not going to explain it, although it's not very hard. But so another part of the theorem. So this theorem is kind of important to us in the rest of the talk. So let me underline it. But there is another part of the theorem which is important. Oops. And it's a converse. So conversely, any U satisfying 1, 2, 3 yields a toric Kähler metric. And what we have, therefore, is a very effective way to parameterize Kähler metrics on the manifold, which are compatible with the toric action. And this is one of the reasons why it's so appealing to do Riemannian geometry on these manifolds. We know how to parameterize the metrics very well. Okay. Okay, so one of the good things about this is that so Riemannian quantities can be expressed in terms of U. So let me give you an example, which again is going to be really important to us. And this was proved by Abreu. And so suppose you have your toric Kähler manifold, then he showed that the scalar curvature, the Riemannian scalar curvature, is given in terms of the symplectic potential by this formula. I'm summing over repeated indices. And this is called Abreu's formula. And it was really important in Donaldson's proof of the existence conditions for toric Kähler surfaces. Okay, and so let me just move on to my next topic, which this is a good place to introduce it. Okay, so this is sort of, this is not it's outside the toric realm. What happens is, this is a general thing in geometry. People want to have a canonical way to choose metrics. And in Kähler geometry, Calabi came out with a really great definition of something that is canonical. So let me tell you what it is. This definition only works for Kähler manifolds. And let's say for now that the manifold is compact. Then omega is said to be extremal. We now say Calabi extremal sometimes. If it is a critical point for the following functional, which we now call the Calabi functional. And the Calabi functional is defined on the cohomology class of the Kähler form. That are in the same cohomology as the given form. And it takes a symplectic form or a Kähler form, and it associates to it the square of the Kähler curvature. Okay, is this clear? It's any critical point of this is a Calabi metric. And so when you write the Euler-Lagrange equations for this, which is again a really good exercise in Kähler geometry, you conclude that G is extremal if and only if the following thing happens. So the 1, 0 part of the gradient of the scalar curvature needs to be holomorphic. And well, one of the reasons why I want to say this is that this definition works in the non-compact setting. So a metric satisfying this is what by an extremal metric when the manifold is non-compact. And you see straight out that a constant scalar curvature Kähler metric is extremal, because if scalar is constant, then this vector field under the yellow bracket, above the yellow bracket, is 0. And so, of course, it's holomorphic. Okay, and so I guess one of the fueling questions in Kähler geometry in the last, I don't know, in the last 30 years has been, are there always extremal metrics? Oops. Oh, let me not do this again. Cancel. Are there always extremal Kähler metrics in a given cohomology class on a Kähler manifold? Okay, and we know that the answer is no, but actually we know quite a lot more, and so what we know in many cases, but I think in full generality, it's still a conjecture, is that there is a way to test whether there exists Kähler extremal metrics. So suppose you have a Kähler manifold. It admits an extremal Kähler metric in here, if and only if it is what's called case stable, which is not something I'm going to explain. The only important thing to me is that you understand that some Kähler manifolds don't admit extremal metrics, and that it's hard to decide. It's kind of hard, or it can be kind of hard to decide when a Kähler manifold admits an extremal metric. So this is hard to define. And it was hard to come up with rigorously. It has only been made rigorous in about 2000. It was only made rigorous in about 2006. Okay, so let me just finish with one quick sort of theorem, which is the following. So suppose you have, so I'm going to do what I will be doing constantly. I'm going to ask, how does extremality play out in the toric setting? Suppose you have now not just any Kähler manifold, but a toric Kähler manifold. Then Abreu showed that omega is extremal if and only if its Kähler curvature is an affine function of the coordinates on the moment polytope. So it's pretty easy to decide on a toric manifold whether a metric is extremal or not. You calculate its scalar curvature. If it's a linear combination of the action coordinates, then it's extremal. Otherwise, it's not. And again, this theorem is kind of going to play a role, what I say later. But it's the typical toric theorem that sort of explain why toric manifolds are so much simpler than generic manifolds. Okay, guess this is I guess it's a good place to stop today. Are there any questions?
Any questions? All right, thank you very much.